So this is we're going to start talking about Maxwell's equations. And what Maxwell's equations are is a set of four equations that govern really every type of electrical or magnetic interaction. So James Maxwell wrote out these four equations and put them in one place and said, here is how electrical and magnetic interactions work with one another. Some of the equations he borrowed from other people, some he modified, and some he actually came up with on his own. In the end, what these equations show is that electric and magnetic fields, and really electricity and magnetism in general, are both very deeply connected. We would actually say in physics that the fundamental force here is electromagnetism, that they're really essentially the same force, just acting in different ways. So let's look at the equations and look at what they mean, and then what consequence they really have when we start talking about the equations. So the first two equations that he has are Gauss's law. The one on the right is Gauss's law for electric fields, which we worked with quite a bit when we talked about electric fields. The one on the left happens to be Gauss's law for magnetic fields. The main difference is that these basically talk about how we could calculate electric or magnetic fields using electric or magnetic flux. Gauss's law for magnetism essentially says that you can't have a magnetic monopole. If you have a closed surface, the amount of magnetic field entering the surface, the amount of magnetic field exiting the surface are the same. So the net flux on a closed surface is zero for magnetic fields. What Gauss's law says is for electric fields, you can actually calculate an electric field using Gauss's law because you can have monopoles, things that are positively charged and negatively charged. So these are the first two of Maxwell's equations. Gauss's law for magnetism essentially says that magnets always have a north and south end. Gauss's law for electric field says, here's a way to calculate electric field using electric flux. The second equation is the law of induction. This came from Faraday, and this really says that if you change the magnetic flux through a loop of wires, you induce a magnetic or an electric field. So changing magnetic flux induces an electric field. The way we kind of looked at it when we first talked about it was this equation on the left, that EMF is equal to the change in magnetic flux. But if we think about what EMF really is, it's a voltage. And how do we calculate voltage from electric field? Well, you integrate it over a distance s. And so really the equation on the right is the way Maxwell modified Faraday's law of induction to fit electric fields. Essentially what this says is if you change the magnetic flux in a loop of wire, you induce an electric field in that loop of wire. So changing magnetic flux induces an electric field. Now what Maxwell did is he actually went one step further and looked at how does changing electric field affect magnetic fields. And he found that there's a similar law of induction for magnetic fields as there is for electric fields. So Maxwell came up with his law of induction, which says that changing electric flux induces a magnetic field. So kind of the odd thing here is that you have Faraday's law of induction, which says if you change the magnetic flux, you induce an electric field. Well, that in turn changes the electric flux through a closed loop, so you induce a magnetic field. So these two are working together. Now, we've seen Maxwell's law of induction before. Another way that we can induce an electric field is by having, or a magnetic field is by having a current. If we really think about what current's doing, moving charges. So magnetic field can also be created by a current. And so Maxwell said, well, we know how currents induce magnetic fields. That's Ampere's law. B dot ds equals mu naught times I enclosed. And what if I just add my equation to this equation and see what we get? And this actually works out very, very well. What we get is an equation that says you can do two things to induce a magnetic field. Have current going through a closed loop, but you can also be changing the electric flux through that closed loop. So both of those things induce a magnetic field. So if we actually looked at what this would look like, here are the two forms we see this equation in. The form on the left has electric flux on it. The form on the right has this term ID in it, which is what's called displacement current. Essentially what displacement current is it's the effect on current that changing the electric flux has. If we think about what changing the electric flux is doing, you're really changing how the electric field acts in a substance. So you're going to have a current that's induced for that change. It's actually what we consider to be a fictitious current. It doesn't really exist, but mathematically it's a nice model to put in our head to describe this system. So the quick summary of Maxwell's equations are that Gauss's law are the first two equations, both for magnetic and electric fields. We have the Ampere Maxwell law right here for induction. How do you induce magnetic fields? And really you can do it a couple ways. Move charged particles around, current, or change the electric flux. And then how do you induce electric fields? Well, you change the magnetic flux. So what's an application of this that we see in the real world? Probably one of the most useful applications, and one of the ones that we deal with on a regular basis, is what's called an electromagnetic wave. So an electromagnetic wave is a wave made up of electric and magnetic fields. It is essentially a changing magnitude of electric and magnetic fields. And how this works is, as the wave propagates forward, you have an electric field which is changing, which changes the electric flux, which induces a magnetic field. So then you have a changing magnetic field, which induces an electric field, which changes magnetic flux, induces an electric field, and so on and so on and so on. It self-propagates. So essentially what an electromagnetic wave is it's a wave of changing magnetic and electric fields. The changing electric field induces a magnetic field. The changing magnetic field in turn induces an electric field. And so we end up with something that looks like this if we were to draw a picture of it. Now the one thing to point out is that in electromagnetic waves, because of the directions of things, the electric field and the magnetic field are always perpendicular to one another, and they're also always perpendicular to the direction of travel. That here the wave is traveling left to right, the electric field is up and down, the magnetic field is forward and back. Now what are electromagnetic waves? Well, they're all sorts of things. You've probably heard of the electromagnetic spectrum before, things like X-rays and gamma rays and visible light, UV, radio waves, infrared, microwaves. All of those are types of electromagnetic waves. And if we were to look at all of them, essentially what they are is changing electric and magnetic fields. What changes what one looks like compared to the other one is the frequency at which they're changing. And what changes how strong they are is the amplitude of those waves. Now what is kind of cool with the electric and magnetic fields is that in an electromagnetic wave, the magnitude of the electric field is always much stronger than the magnitude of the magnetic field. In fact, if you actually go through the two laws of induction and kind of figure out what does this actually mean, you find out that the maximum magnitude of the electric field divided by the maximum magnitude of the magnetic field always gives you a constant, and that constant happens to be c. Now, that at first glance may seem kind of odd, but this actually kind of looks like the velocity selector as well. That if in a velocity selector, if you take electric field strength and divide by magnetic field strength, you get the velocity of the particle. In this case, the velocity of the particle, or the wave, is the speed of light, c. Now there's one other weird thing that kind of pops up when we play around with these equations, and that's that the speed of light is equal to the square root of 1 over epsilon naught times mu naught. So if epsilon naught or mu naught somehow got changed, the speed of light would also change. This would suggest that the speed of light is really very intimately connected to electric and magnetic fields and how electric and magnetic fields travel through free space, which probably shouldn't be all that shocking, because what light really is electric and magnetic fields traveling through free space. So that kind of gives us a quick overview of Maxwell's equations and looks at one place where we use them to describe what's happening in a setting, in this case the electromagnetic wave. That essentially concludes all the lessons that we have for the AP curriculum. Maxwell's equations is kind of the last topic we talk about, and so that concludes the set of lessons that I have.